Large language models are capable of many different tasks. You can roleplay with them, ask them to generate code, and even write poems. But in some cases, we want to customize them or have them specialize in a particular task, like generating code in C or speaking a really niche language that wasn't in the original training data. This is where fine-tuning is useful. This means further training of the model, actually updating the weights and biases using gradient descent, except this time we're using a new dataset, typically much smaller than the original dataset, and we start off with the pre-trained version of the model. Although some models like GPT are closed source, many models like the Llama family from Meta are open source. You can download the model weights, chat with the model locally, and even fine-tune it on a personal dataset. But these models have billions of parameters, so how can you fine-tune them without the expensive GPUs used to pre-train them? The answer is LoRa. Now that the NPCs have clicked off the video, let's get into it. If you're still here, you're the kind of person I would want in my ML community, which I'll talk about at the end. Back to LoRa. There are some other tricks like quantization, but low-rank adaptation is almost always used for fine-tuning. There's two main questions to ask. First, of the billions of parameters in the model and all the layers, are all of them necessary to update? The answer is a resounding no. We can achieve almost the same performance by freezing most of the weight matrices and only updating the ones used in the attention layer, one of the core components of an LLM. The second question to ask is, for the matrices we update, do we actually need to directly update each entry through gradient descent? For an n by n matrix, that's n squared total parameters, and n can be in the thousands for LLMs. So we can make a second simplification that achieves almost the same performance. Freeze the original weight matrix, W0, let's calculate delta W and add it to W0 once fine-tuning is complete. W0 is the product of two smaller matrices, B and A. B is n by r, and A is r by n. The entries in B and A are the ones updated through gradient descent, and this is only 2 nr parameters. R is typically much smaller than n. If n is in the thousands, r might only be, say, 16. Dropping the constant factor, this is on the order of n entries to update, which is far less than n squared. By the way, the original LoRa paper recommends initializing B to 0 and A to a normal distribution for optimal results. Side note, if you're interested in an end-to-end walkthrough with every line of code explained, I created a full course on fine-tuning, exclusively for the students in our ML community. In addition to requiring far less compute, there's another benefit to LoRa. Let's look at a tree where we have different versions of an LLM, each serving a use in production. The most intensive step here is loading the root model into memory, but that only needs to be done once. To switch between customized states of the model, we simply add and subtract delta W, which is just the product BA for each node in this tree. Adding and subtracting these smaller matrices is far less intensive than reloading the full model, which is billions of parameters large. LoRa is incredibly easy to use on free GPUs, like the one provided in Google Colab, and will likely be used for years to come. If you found this video helpful and are interested in more fine-tuning videos, leave a comment, and I'll see you soon.